dressed, didn't realise. Good morning all. So, welcome to Grown Up School. Third year design project, design appraisal. Don't forget that CRE has coursework next week, compulsory attendance. Yep. There's a test in a minute. I did say welcome to Grown Up School. Don't look so shocked. So, not as many faces as perhaps I'm expecting, since I've got 3 boxes of books, but never mind. Who knows if this is working, but I'll try to be good on microphone. I'm not known for it. Ooh, we've actually got a user guide, and we've actually got a box of pens. That's an improvement on the last 3 years. So, I'm a bit hot and sweaty, apologise. I had to go and get my own handbooks out of Reprographics this morning, so I'm a little bit stressed, but I'll be okay. So, Thursday night still takes its toll on the student body, I suspect, but never mind. Such is life. So, CRE3, welcome. Catalytic Reaction Engineering. We all are chemical engineers in here, are we? Yeah, we'll find out soon enough. So, to start off with, I thought I'll give you a nice welcome lecture and then tell you some good news. There's no class this afternoon. So we would normally have a 2-hour session, 2 till 4, but you probably all read your timetable and there's no class. That was deliberate, just to give you time to settle in and also to start looking at the handbook and prepare yourselves for next week's onslaught. So we will do a coursework next week. We will do a coursework the following week. It'll be marked and handed in at the end of the session, 2 weeks in a row. And then the third bit of coursework, you will be assessed on some posters that you will prepare, except not posters on the environment this time, posters on particular catalytic reactions that are of importance to engineers. So the reason for doing this is, number 1, wake up, it's year 3. Number 2 is, it's out of the way before you get stuck on design project. That's the main aim. It's also worth 20%. Average score last year was 71%. Average attendance was 96%. So I'm preaching to the converted because all the people in the room are here, but those of you who know are not here, please advise them that if they do not attend, they will get 0. And there are no excuses. So that microphone's working. Don't know if this one is. So do me a favour, sign in. You've got a rather large list to look through, which is just that that's what I got off the lady in the office. No problem. Boki, you can start your list off. So it's a nice class. Later on in the course is my specialist topic, so I expect you to get a little bit lost towards the end of the course. Bless you. Who am I? I'm an international expert in catalysis. I'm one of only 4 people in the UK doing the sort of work that I do. I'm one of only about 30 in Europe doing what I do. I've got specialised lab facilities that link directly into catalytic reaction engineering. So those of you here next year who are interested in dissertation topics, my lab is kitted out with the sort of equipment we'll be talking about on a bit of paper during this course I actually use in my lab. Any of those of you who wish to have a tour of my lab, which is a very small lab, so I can only do small tours, just have a look at what the kit looks like. I can do that. I've also got a couple of video clips which I'll show you of bits of kit. Most important thing is to prepare you for design project. The coursework prepares you for design project. It relates to CRE3 and hooks to lots of things in CRE3, but the main function is to get you looking at literature, getting you appraising literature and telling me what's the good bits and the bad bits. Last year I ran it for the first time. It was universally scary at the start, but by the end of it everybody had the marks and everybody was quite happy, and in fact it was voted the best piece of coursework. It was so good that Megan used it for the postgraduate students, and she now has a full 10 weeks of the same sort of activity. So Megan Jobson taught you process design simulation last year, I think. Okay, so forget I'm head of teaching and forget that I shout a lot. I do. I also make bad jokes, try to be nice and laugh occasionally, but let's get on with the course. Okay, so if you're in the right place and you look a bit light on numbers, please sign in. Do yourself a favor and don't sign in for your mate, because I can actually count the number of people in the room, and I actually want to know how many handbooks I've now got to carry back to the mill because you're not here. Okay, so I've got 3 boxes. So, what's the course about? I think it's important first to look at catalysis and then look at CRE2. And remember that CRE2 you didn't do so well in. What was the average in CRE2? Was it one of those papers that got put down, or was it one of those that stayed flat? Do you remember? Was it scaled up, scaled down, or did it stay flat? Scaled down. Whoa. So it was too easy then. The reason for that is the coursework usually gets a very high average. You don't get a high average in this coursework, and you have to work for your marks. Okay, so that's the key thing. I am generous. I have 6 laid-on demonstrators who are experts in their particular specialist topics, and those are the specialist topics you'll be looking at. So we'll do that next week. Don't panic about it, just turn up. That will be the 2 till 4 session next week, James Chadwick. And I can see from the outside of the building that fire regulations are hitting everybody, since all those partitions you notice down in the foyer are actually gone up overnight over the last 3 days. It's quite interesting. So I have a test there which we'll do in a minute. Let's just get to know one another a little better. Those of you who had environmental last year know me already. So to start, introduction to catalysis. So there's some design equations you need to remember. You need to remember what activation energy is, and conversion and selectivity. So I'm going to help you with that. Let's have a look at the handbook, and open the handbook if you want to. If not, just look at the slides and away we go. So, top equation, what's that? It's a design equation for a PFR, very good. Plug flow reactor. So you just put PFR next to it, and then you can revise the notes in CRE2 if you need to. Trust me, you don't need to. What's the one next to it, underneath? Say again? The one at the bottom, what's that one? That's a CSTR. So what's the one in the middle? Who said that? So you obviously got above average and got your mark scaled down. The other answers obviously needed to be scaled up. Wakey, wakey. So that's a recycle reactor. Indeed it is. Since when did the nice little simple CSTR equation look like the one in the middle? It's a recycle reactor in the middle. It's important to remember, how does a recycle reactor turn into a CSTR? Not the same gentleman at the back, by the way. Glad to see the back row is got the bright ones on it. I'm looking at the back row over there now because he's made you look bright. So what do you want to do to make it? What do you? How? Say it again. Yeah, you recycle it, but how many times? A little, a lot? So full recycle. Okay, so he's absolutely right. So what you want to know is that R, the recycle, is actually as high as you can get it. So if you had a recycle of 1, it's basically a straight through reactor, which is a plug flow reactor. If you then have it at anything up to 20 or anything like that would give you a CSTR. Come in, young man, handbook at the front. Try not to be late next time. So you've written all that down, you've remembered it. Those of you who got the wrong answers. Here you go, here you go. So it's important to remember that you don't change equilibrium. You only get there faster. So there's 2 types of reaction in catalysis. There's a homogeneous and a heterogeneous catalysis. Different types of reactions, very important reactions. Okay, so if we're looking at those, they don't look particularly exciting, but ammonia synthesis and methanol synthesis were the mainstay of ICI and the business that ran for over 150 years before it broke itself up, and they are the mainstay of generating chemicals and intermediates. So Very important. Now, they use catalysts. What are catalysts? So some kind of substance. It's important to note that a catalyst increases the rate of reaction and it doesn't change anything else. That should be A-level stuff. But I'm reminding you because it puts the context onto the course. You can have different types of catalysis. You can have molecular catalysis, surface catalysis, homogeneous catalysis, and heterogeneous catalysis. Homogeneous catalysis is same phase. Heterogeneous is 2 phases. Good. Okay, so we've got some knowledge and we're remembering it. So these catalysts that you see there, I have some of them in my office. I have the actual ICI catalysts. Some of you have got friends, perhaps in 4th year, who may have worked at Johnson & Matthey, for example, in the Clitheroe site. Actually, I'm trying to remember. I'm not sure if there is anybody at the Clitheroe site, but they actually make the catalysts. They also employ you lot. So I think the last 2 people who were on placement there have got jobs and they're based at Clitheroe. And they're actually physically making the catalyst. And it's very basic stuff. Dig a hole in the ground, dig out some iron ore, treat it with acid, make it into the oxide, make it into the catalyst. That's it. It's very basic stuff. Very interesting for me as a chemist and having done catalysis a long time. So I just thought I'd put that list there for you to read. Not necessary for me to articulate all of it. But some of the silly things you do answer when I give you multiple choice questions or questions in an exam paper, and I do short questions so that you can get some marks straight off the bat. Average for CRE, by the way, is usually 64%. I did get scaled down once in the 14 years I've been here, and I taught CRE1, CRE2 and CRE3 in the time I've been here. And I got scaled down, I think, last year or the year before because I misbalanced the question and you murdered one question, or that class murdered one question, and then they didn't do very well on the other, but it was too late. The average was very high. Key things you get wrong. The catalyst does not affect the thermodynamic affinity of a given reaction, simply that it affects the rate. So what happens to delta G or what happens to K equilibrium? Say that more confidently. Anybody else who didn't hear that answer? Okay, so I said it already. I gave you the answer. It does not change. You can only strive to get equilibrium. All that a catalyst will do is get you there faster. Okay? Just imagine me and Usain Bolt running 100 meters. He's got the catalyst because he knows what he's doing and he's there before I even make the first 10 meters. Okay, so that's the kind of thing you're looking at, is catalyst. Catalyst accelerates but gets you to the same point, the finishing line. Since the catalyst enhances the attainment of equilibrium, it must accelerate both forward and backward reactions. The question is, name a good hydrogenation, dehydrogenation catalyst. Don't expect you to do it now, but you may be able to do it shortly. Or you can look me up and see what work I do, because I use the standard dehydrogenation catalyst. Although not involved in stoichiometry or thermodynamics, a catalyst is involved in the mechanism. That's what I want to just approach today. Okay? What does that mean? You're all familiar with these kind of diagrams. Certainly I was when I was at school. But things change, so maybe you've seen them in CRE1 with Sam Davissa or with someone else. So what have you got? You've got the standard catalytic reaction. So look at the graph first. Just look at it and look at the E activation energy, which is the one for nitrogen adding to hydrogen, and you've got a homogeneous activation energy, and the homogeneous activation energy is 55 kilocalories per mole. Stick a catalyst in and you change the pathway. So you're going from the top line to the one at the bottom. Notice it's got extra steps. It's got extra steps. Those are mechanistic. So it's changed how it reacts, but it still gets to the same point at the end and still makes ammonia. It's just a lot easier for it to get there. So it goes faster. Once you've got that in your head, I don't need to say it anymore, and you just remember it. So when you're doing design projects and you're looking at a new process and you want to find a catalyst for that process, you'll have loads of catalysts and you'll be totally confused because there'll be 20 academics just like me working on maybe 3 catalysts each. So that's 6 catalysts, 60 catalysts in total that they'll be researching on, and you'll be looking at it going, well, I don't understand. I've got these papers all over the place, millions of them. Which one's the best one? So what you do is you go back to something like Ullmann or Kirchhoffner, which are the standard encyclopedia of reactions, and they're electronic as well as hard copies in the library, and you look the process up to see what is the standard process. And you compare the standard process to what you're innovating along. Basic step in about 3 weeks from now for your design project. Okay, you're a good class, I like it, you're very quiet, you're quite attentive, and you know some of your stuff, so that's good. Let's not bore you. Let's just remember something else. So this is an equilibrium reaction. So we're increasing the pressure here. So we've got equilibrium conversion against temperature. The equilibrium of the reaction rates is determined by the thermodynamic feasibility and not by the catalyst. Why is high pressure favoring the reaction? Anybody who's not played so far? Come on. Yes, sir. You haven't got a handbook, but so there's more molecules on the right, on the left-hand side, the right-hand side, yeah. So there's a lower number of molecules on the right-hand side, and pressure therefore favours that. So if you increase the pressure because you've got more molecules on the left-hand side, yeah, you started the wrong way around, but you were saying the same thing, yes. So just to remember that pressure. So when you're designing a process and somebody asks you the question, should we pressurize this process? Just do the simple thing first. Look at the number of molecules written down on stoichiometry. See which one is likely to work. Think. Use your brains. You're very good. You're highly technical, but what you haven't done is join up the basic dots. I'm trying to help you with that. These are the most common questions that get asked in design groups. More importantly, these are things for life to just have in the back of your memory. That's all I'm trying to get across. Will I test them? Well, I might. But I'm thinking you should get this because you'll have done design, therefore it'll be too easy in an exam paper. So we've gone from 10 atmospheres to 100 to 300 to 700. Significant differences in conversion as you've gone up in pressure. But note that you could do 300 atmospheres and it's not far away from 700 atmospheres. So as design engineers, you might say, well, yeah, I know I get the best pressure, but it might be too expensive to get that pressure. And then I've got the ancillary equipment and monitoring and the danger everywhere around. I might want to use a slightly lower one. So you can think, you can go with the basic rules, but you must get your fixed point now, as I need to understand how I'm going to design a completely new process from scratch. Do I use pressure? Don't I use pressure? Do I use temperature? Don't I use temperature? Do I use a catalyst? Don't I use a catalyst? These are the basic questions first. Start with simple prepositions and then work to complex. Start with a black box. Things going in, things coming out, don't know what's in the box. You can do a heck of a lot that way. Methanol synthesis. Look at the reaction. There are some questions, and maybe in the handout I haven't written those words in red, so just check if I have or I haven't. But wait for the second that I've explained what I'm doing before you go to the pen. So, carbon monoxide and hydrogen react over methanol, copper and zinc oxide. It's a greenish catalyst. I can't swear because I'm on tape, but it's a very chunky catalyst. Let's put it that way. It's a chunky catalyst with a hole down the middle of it. You will see, oh, they're just pens, they're not marker pens. So yet again, I've got no marker pen. I was rash in my expectation that I would have something to write with. It's a good way of not having to clean the board, that. Don't supply you with any pens. Anybody got a dry white marker? A very good class last year, one of them had one. Damn. So, it's basically a Rashid ring. If you remember what a Rashid ring looks like. Do we? Yes. Who said yes? You can come every week. So, that's good. I'm not asking you. Good. So it's basically a little cylinder with a hole drilled in the middle. I'll bring them next week so you can have a look at them, okay? But this is your warm-up class, not the show and tell class. We'll get to show and tell later. So, why did they choose the catalyst? Because it lowered the activation energy, therefore it made it easier. Is it exothermic, endothermic, or too simple a question? So when you look at a reaction, and you look at a global reaction, you always go, and up to this point we've gone A plus B gives us C. That's all we've done. Remember, I taught CRE2 for 10 years, and now Phil and Aileen do the same course. Okay? Straight out of Octave Levenspiel, if you didn't already know that. Okay. So it's classic stuff. A plus B goes to C. Right. What's the order of reaction with respect to CO? Just as you do in kinetics. Let's see who's got the bright bits and remembers.
1.
Correct. What's it with respect to hydrogen?
2.
And why are you making that assumption? What's the key sentence, the key word that you're looking for? You're basically treating it as an elementary reaction. You're assuming it's doing exactly what it says on the tin. When somebody says elementary, or what assumptions am I making? You're making, this is a CRE3 handbook. Why? Because it says so on the front. You make the most simple deduction you can, and then you look to see how complicated it gets. That's the way to approach design. That's the way to approach this class. So, is it exothermic, endothermic, or is it too simple a question? The answer is it's too simple a question. There are too many steps buried in that simple reaction. It does look first order with respect to CO, and it does look second order with respect to hydrogen. What would happen if I put a large excess of hydrogen in the system? It would, but don't you answer. So what would be the overall order of the reaction? So it's 1 with respect to CO, it's 2 with respect to hydrogen, but now we've just flooded it with a massive amount of excess hydrogen. It does work, this process, with an excess of hydrogen. So it's pseudo first order is the word. You were right to say 1, but that's the correct answer. It's pseudo first order. So we're already trying to pull back our memory of first semester from CRE2, and we're not doing too bad. Some people are with it straight away. Some people are still going, oh, what is he talking about? That's okay at this stage, because this is introductory. We're not doing anything too taxing. We're just trying to get your memory jogged so you can look it up. You've now answered at least 5 of the questions in the tests. Just so I'm trying to reinforce it. The test should be online, but I had a slight technical hitch. I'm very illiterate with computers, as you know. So consequently, I didn't manage to upload it in the way I wanted to, so I'm going to give you a paper one, and then you can all have a go, and we can give you the answers next week. And then we can argue about one which is wrong. Okay, so there is a wrong answer within one of the questions. You'll get the right answer, and then we'll give you the wrong one back. Anyway, let's worry about that in a minute. So, homogeneous reaction, follow the steps. Do we all understand the graphs now? We're looking at energy levels. We're starting at a base point. We've got CO and hydrogen. We then are giving them some energy. They're then dissociating. Notice the hydrogen at the top is dissociated. Then it's linked onto the CO in the next step. And then further a hydrogen comes on, another hydrogen comes on. Then another hydrogen splits. And then we get methanol. So not one-step process, actually a 1, 2, 3, 4-step process. All we're talking about here is reaction coordinate. Don't be confused or not know what it is. It just simply means we're traveling in a timeline this way. It's as the reaction is proceeding this way. So it all got messy. We put a catalyst in place. We dropped the activation energy considerably, notice. So now we've got a palladium catalyst that's doing the job. We don't know anything other than it's palladium because it's got PD on the bottom. There are a few chemical symbols within this course, but you'll find out soon that the ladies will always remember what the catalysts are, because they're palladium, they're platinum, they're gold. They're usually precious metals, okay? Boys, you generally mess around in the muck and the dirt, so you'll remember the other set of catalysts, which are usually iron, copper, zinc, so things you dig out of the ground. If you remember it in that way, you'll not have any trouble answering the question, name some typical catalysts for these processes. Okay? Smile, it's not that difficult. So, palladium. Palladium, hydrogen, what is it doing? It's not seem to be doing a lot here. Oh, but the CO is absorbed on the surface. So now we've got an absorption step. Because we've got a heterogeneous material, we've not got a homogeneous material where it's all gas phase. We're now sticking a molecule of CO onto the surface of the catalyst. Our CO is stuck to the catalyst, so we've got an absorption step. We'll have some kind of mass transport because we're flowing something past the catalyst, and the CO has got to get from that across the boundary layer to the catalyst to absorb on it. So these are starting to build the catalytic steps. This is what's in this course. So now we've got the absorption, we're now absorbing the hydrogen, and as it absorbs, it splits. So now we've got multiple sites and absorption. Next we've got the linkage like you saw before, the double linkage, but look, you've now got both two sites occupied. So now we're talking about sites. We're talking about active sites on the catalyst. So this molecule of CO whizzes in and sees a very attractive site, and it sticks on it. In the process of doing it, it's done some transformation, or maybe it's just holding it on. So now we're going to talk about active sites within this course. That comes up in Langmuir and Hinshelwood kinetics, which blow your mind usually. What you should be thinking is, it blows your mind, but once you've done it 3 or 4 times, you remember it for life, sadly. And everybody relates models to a certain kinetic model. And Langmuir, Hinshelwood, Hugh and Watson, which is LHHW, and LH for Langmuir, Hinshelwood, won Nobel Prizes for the various people. And that's a long time ago. And we're still using them today. Okay? So we've got mass transport, absorption, sticking on something called an active site that we need to know about, and we're talking about how the kinetics work on a surface controlled reaction. That's all CRE3. You end up over here, to cut a long story short, and you've got your molecule. And all it's done is reiterate what we said about ammonia synthesis. It's done exactly the same thing, except now we're doing it for methanol synthesis. We've dropped the activation energy. Have we affected the equilibrium constant? Good. More of you would be nice joining in. But no, because that's the thing. We just made it go faster. It's easier to do. We need less energy. If we need less energy, class, what does that mean? Why? It came from over there. I wasn't looking. Somebody said cheap. It's cheaper. Why? Because you have to heat it less. It doesn't have to go to such a higher temperature. So you've saved your energy burden. Your energy on a plant is key. Key thing about the methanol synthesis plant, since I designed one in July, so I did the design project in July, design for grown-ups, or design for remedial class, whichever way you like to look at it, is that there's a balance between the hydrogen that goes in and the CO, because you produce steam that drives the turbines that help you generate the energy that keeps the process balanced. And there's a very key ratio that operates at, and it's different at different plants in the world. So it varies between something like 2.5 to 1 to 4.5 to 1. But that, and we had to pick one, and we picked the one that balanced. By good fortune, we did not know when we were doing it. Okay. How are we doing? Not bad. Maximize conversion. Do you remember what the equation looks like? Some of you will, some of you won't. Go look it up and write it down. But x equals CA0 minus CA over CA0 is a good one to remember. X equals CA0 minus CA over CA0. So concentration in minus concentration out divided by the concentration in. Maximize selectivity. Now there are lots of different ways of expressing selectivity. If you go to Wikipedia, you will see a way of doing it. In the past, Wikipedia has been an unreliable source of stuff, but it's getting better. It's getting a lot better. So you can have a look at what it is. But basically, yield is the thing you want, or selectivity to the thing you want, divided by the amount of conversion that you've had. So in other words, how much have I converted? 10%, 20%, 30%. How much is the selectivity, let's say, to molecule A, or methanol in this case? Then it's the amount of methanol that produced over the number of moles that are converted. Okay? So it's actual conversion, converted moles, with the nominator being the amount of the thing you want. Go look that one up because you're not so familiar with that. Is it going to be a major deal in the course? No, but it will be a major deal on your design projects. So it's good to think about it now and just have a basic expression. Go look it up. This class is going to have to do a lot of thinking and a lot of looking things up. It's not because I'm trying to make you work. It's because you need to have this basic toolkit as you do design project next semester. This semester's kind of an easy ride on design project. You won't think that when you're doing it, but it is. Now then, the question, is it always possible to maximize selectivity and maximize conversion? Okay, let's think of it another way. What do you think the optimum conversion should be in any process?
Depends on the process.
Park that. Anybody else? So the front have said, depends on the process, which is the correct answer. But you would have thought that you'd like to maximize conversion up to 100%. And you spend a lot of time in the lab trying to do that. But engineers know that when you take something that is a few grams and scale it up to a few tons, there's a lot of things go in between, and one thing is for sure, you're not going to get the same conversion on your plant that you got in the lab. So you find yourself with processes that operate at 10% conversion. There are processes that are economical at 10% conversion, which is scary because you've got 90% recycle, or you've got 90% separation costs if you're not recycling it all. So that's a hell of a way to go about things. Can you maximize selectivity? You should always try. There is no limit on how selective a process can be. You can get 100% selective. It is extremely rare. But where you're producing methanol, you won't just get methanol, but methanol might be the main product, and therefore you might get the selectivity up. Dehydrogenation reactions are classic at not getting maximum selectivity. Don't worry about the throwaway comments. This is for you to think about now. Which is the best catalyst for methanol synthesis and why? Now look, we said we had a palladium catalyst before, but that's just an example. So where do we start? Have a look at the diagram. We're on the left, as you're looking at it, on the left-hand side, you've got water and methane as a product. You come onto this side of the process, and you've got, on the right-hand side, you've got methanol as the product. You've got two catalysts. Which one are you going to pick, and why? You've got nickel and palladium. You want methanol. Now then, nobody who's answered previously answered. Rest of the class, think about it. Just so you know what I'm like, I'm not brutal. I won't pick on anybody on the first week. But if you look at me at the wrong time, and I'm always in a bad mood when you can tell that I do pick on somebody. Yes, Rena?
Would it depend on the price of each customer?
For this exercise, no. In reality, no. Sorry. You will think about different, if the catalysts were equally matched, costs would come in. If the catalyst was available as a raw material from Russia, you'd think twice. Okay? And the reason for that is catalytic converters, which have platinum as the catalyst, used to have palladium as the catalyst, until one year when the Russians hiked the price by tenfold and everybody went back to using platinum. The best catalyst is palladium, but the major source of palladium is in Russia. And if you want to know whose fingers got burnt, that'll be Johnson and Matthey. Which catalyst? Why?
Because make catalyst water will make condense and catalyst.
No. Correct. I haven't told you any other variables other than activation energy and changing the activation energy. What I added in here was a selectivity puzzle. I said if it goes over to the left-hand side, it's going away. You're losing selectivity. Every time you drive the reaction this way, it loses selectivity. You want it to go that way, so it has to be selective. So that's just to get the selectivity problem into your head. What are we actually talking about? In this process, you do make water. You do make methane. You can't stop it, but you want to minimize it. And the way you minimize it is you go that way. Now, why would you not choose nickel? Because nickel gets to the products easier, and the answer is simply that nickel goes the wrong way quicker. So it'd be the wrong catalyst. So that's the answer. Nickel goes easier to this product than it does to that product, but palladium goes much easier to methanol than it does to those things. So your catalyst must be palladium, and that's it. That's the whole answer. But it's a way of introducing selectivity to you, and I hope it was okay. Doing very nicely. We're at 22. I can give the thing out. Not bad at all. First lecture is usually paced at 40 minutes. Diagram represents reactants absorbing on active sites on a solid catalyst and make CO, methanol, and we need to react with CO. So all that says the same thing as we've just discussed. So if you've got a bit of space in the handbook, just write down what your conclusions were on my discussion. And if you want the posh way of saying it, the correct way of describing what's going on is palladium seems to have a higher energy barrier to CO dissociation. CO dissociation takes you to methane, the wrong way. Go the other way. So it has a... You're paying attention. He looked at me just at the right minute when I was making the statement, so I just wondered if he picked up on what I said. So palladium has a higher energy barrier to making methane. Therefore, it's the better catalyst. Nickel has a lower energy barrier, and that's all that's seen said there. And all I've done is give you a posh explanation of what I just explained. So that can be written down if you wish to, but you should have already articulated what you want to say. It's just a posh way of saying it, the right way of saying it. Palladium has a higher energy barrier to CO dissociation. You write that in your dissertation or design projects, and you'll be doing very well. I'm sorry, Professor Webb, we can't use this process because we have a higher energy value to the production of that. It would be very good. Is that the end? Oh. Carry on writing it down, and we'll stop there for a minute. Just take one and pass it back. Take one and pass them back. Take one and pass it back. How are those tests doing? Are they making their way back fast enough? What are you doing, taking 5? What are you doing? Oh, is that for the end of the row that you're passing them on? Or is that for that way? Why is he taking 5? What are you doing? Come on, get them passing back. You're holding all of them. You'll never last. Yeah, they are different. They're different on purpose. So you're not supposed to take one of each. You're just supposed to take one. Boys, eh? So can I have your spares now if you've got any spares? That's okay if you just pass them back. Pass them back. You can have one each. Keep it moving. Keep it moving. I have to say that it's only 110 of you. God help us when we've got 203 of you. Go on, take one and pass them on. Where's that one got to? Have we made the back? Thank goodness for that. You've got a test. You're all right. Have we run out? Have we got any spares? Good lad. So it's going that way already. Okay. Shh, 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 shh. Keep the hubbub down for a minute. Try not to do it instantly. Should take you about 5 minutes, this test, okay? So you can do it now if you want and have a good go, have a little go, and then you can go away and think about the answers. That's fine. What I want you to pay attention to is there is a timetable in the handbook, okay? So while you're passing that around, just have a look at the timetable. Just keep it, and then we can discuss it next week, okay? You can hand it in if you want to do it now, but there's no rush to get all the wrong answers. Plenty of time to get the right answers. Now what I'll do... Yes, young lady. Hello, nice to see you. No, it's formative. It's to make you remember what the class was like last year. To get you up to speed for this year quickly, there are 5 individual tests. They are different. So if you've got 4 friends with different numbers, get together and then you can look at all the answers and use it as revision. What I aim to do is put them on Blackboard when I'm not so incompetent as I was yesterday when I was trying to do it. Okay. So Blackboard course at the moment is last year's course. By about 11:30 it will be taken down and it will be this year's course, but don't worry about it. So have you got the timetables in front of you so you can just have a look? I just want to talk you through the timetable. So we've got a nice lecture again next week which is a bit soft, and then we're into some hardcore stuff by the time we get to the 6th. Okay? Coursework is a paper review, and I'll talk you through that next week. There is a little note if you go to the coursework page in the handbook, but not now. You go to the coursework page in the handbook, it'll explain what the sort of thing is we're going to do. It is very short, it is deliberately short, and it's deliberately not trying to tell you too much information. Megan's is about a 4-page brief, mine is 3 sentences. It's class for grown-ups. So, just have a look at the timetable and refresh where you are, because it does change. We start off with exercises and tutorials in EBL Suite. Not quite sure why I've got tutorials in Reynolds C9 on Friday there, so that could be an error. I'll check that. Because they should be tutorials, and I don't see why we would come out of the place in James Chadwick just to walk down the road, so I can see a mistake before I even start. So apologies for that. What is the key bit is that after reading week, we will be going to the poster session on the week 7, and then we'll be having lectures in Reynolds C9 at 3 o'clock with a tutorial session down the road after it. Okay? Now what happens is by the time we get to week 7, you're already into design project and starting to go for the exits on my course. Okay? We'll try not to let that happen, because if you do let that happen, you won't be listening to the advice that you're given and where the exam questions lie. But it does happen, and you might not think it'll happen now, but it will happen, because you'll start to panic about what you've got to do for design project. So I apologize, because it should be that all this semester, I think, all this up to reading week, we will be in EBL Suite. will be in here in the morning and EBL Suite in the afternoon. After the break, when we've done the poster session, which will all become very clear next week, you will then go into lectures in the 2 o'clock slot so that I can get through the course and do the thing. But you'll enjoy it because it's a mixture of doing problems by yourself. We used to do the problems in the Reynolds in many rooms next door. So we're going to do it in EBL because there's better space for you to do the exercise on the poster and so on and so forth. Okay? So it's nothing complicated. For those of you who are PGT students now, so PGT students in the room, are there any PGT students? Those of you, the voices of wisdom. 2, 4, anybody else? 5, 6, 7. Science Without Borders, I know, but I don't know how many. So Science Without Borders, young lady. Gabrielle, thank you. Just you two then. You two brave souls. Okay. Okay, so that's not too bad then. So I know how many MSCs I've got. It's about 6. I know how many Science Without Borders who are trying it, sampling it. That's 2. Everybody else is a card-carrying chemical engineer doing third-year design project. Okay, so the test. You can have a look at tutorial 1 if you wish, between now and next week. Of course, the moment I say that, I know what's going to happen. However, it's good to get a little bit ahead of yourselves. Look at the handbook as well, and you have some reading material at the back. Everybody goes, oh no, we're not. Is that on the exam, Dr. Garforth? Please. Is that on the exam? And I will say elements of it are examined, yes. Which is code for, you've got to read it. Now, some of it is unintelligible to you, but will get intelligible. What I suggest you read is by a book by my friend Bob Ferrato, which hopefully she's not omitted. Okay, so as you go to the back, there are fundamentals of catalytic processes by Calvin H. Bartholomew. I think Calvin died of cancer last year, so a sad loss. Bob Ferrato is my referee for promotion, just so you know, but he also wrote the book on industrial process, which is about this thick. It's an extremely good book, but it's not necessary for this course. But if you go into a catalytic job or you go into a process technology, you want to buy, yes, hold it up if you wouldn't mind. So that book there is a superb book. I ordered a few copies for the library, but it's meant for reference. It might help you designing your processes, but it's not meant for you to go out and buy. But it's nice that you brought it because it saved me carrying it and showing everybody. So the chap that wrote my reference this year for promotion, okay? So you know who he is. And that puts me into context as well, I think. Okay, so, lovely man, absolutely lovely man. He's 70, he's a professor at Columbia University now, but he worked for Engelhart Catalysts, which has now become BASF, and he worked there for about 30 years as head of the research. Very big guy, very big scientist, really lovely man as well, which often goes hand in hand, I think. Okay, ladies and gentlemen, I have finished for the day. You've finished for the day as far as catalytic reaction agents. So in the time that you have this afternoon, if you do wish to use it wisely, have a look through the handbook, have a look at tutorial 1, and do the test. The test is not assessed. The test is for you to help learn, to refresher. So there are 5 tests in total. Yeah, but you don't need it for the course. It's just a good reference text for life. And there's lots of copies in the library for you to have a look at. But that is a nice introductory read. Okay? Oh, thank you very much. Thank you.